So we're going to begin this journey into vectors, a very useful thing. Let's go back to this idea of translation of graphs to try and explain why we have vectors. Basic parabola y equals x squared. What I want to do is I'm going to translate it 2 units to the right, then up 1. What's the equation of our new parabola? So there's the original one, y equals x squared, and we'd go, okay, I'm going to move that to the right 2, and then up 1, it's in this new position. And what we've seen is basically what we've done is, well, when I moved it to the right, x squared became x minus 2 squared, and then when I shifted it up 1, it then became x minus 2 squared plus 1. And so that became our new equation, y equals x minus 2 squared plus 1. I could do it a different way. That first one was done by doing a horizontal, then a vertical. Well, I could do it all in one hit. Just move it diagonally. And that thing that I've just moved it along is what we call a displacement vector. The nice thing about it is that vector remains the same, and that's why we like using vectors, because it doesn't matter where I move it to, it stays the same. It never changes. So I could have moved all of these different points, but you'll notice every one of those points has been moved along that same vector. That's the beauty of playing with vectors. I could write it this way then. This is what's called column notation for vectors. I'm using capital X and capital Y for the new equation so I don't get confused with what's the old one and what's the new one. So I'm saying, hey, this new one of capital X, capital Y, what I've really done is I've got the old one which had coordinates, the vector x, y, plus I've now added this new vector here where I've shifted it across 2, so the x value 2, and up 1. Now, what I've really done is created a set of parametric equations, because I know that the old one, y equals x squared, I could have written in parametrics like that. I could have said, well, x equals t, y equals t squared. That would describe y equals x squared. So now my new one is t plus 2, t squared plus 1. So if I want to find the equation of the new one, I just play around with the parameter. I've got to eliminate the t. So capital X is t plus 2. Rearrange that, make t the subject. Substitute that into capital Y, and look what we get. It's exactly the same equation. So it's just another way of doing it. So I use that, I guess, as an illustration of how vectors can be useful. So some definitions. There it is, there's our vector. That's what's called a displacement vector. I'm displacing P to Q. Now, the order that we write it is important, because the first letter is saying, hey, I'm moving the P, I'm shooting it to Q. And then the arrow on the top is telling us, well, that's the direction we went that way. P we call the tail, and then Q we call the head of the vector. Some other notations for that. The first notation, which we don't really use that often, because when you're handwriting solutions, how do you make sure that's bold? Other than going over it and over it and over it, that's just messy. It's too easy to confuse that. But you might see it in texts, so where it's been typewritten, things like that, they might use a bold letter for the vector. More commonly, you'll see P with a tilde underneath it. And that's really important. You make sure, if you're talking about the vector, you put the tilde underneath it, because the vector P is very different to the pronumeral P. If you don't put the tilde underneath it, then we're going to assume, oh, you're talking about a pronumeral. You're not talking about the vector. Every vector is uniquely identified by its length, which we call magnitude, and the direction that it goes in. And that direction is always the angle we make with the horizontal, similar to what we saw in trig. When we're finding slopes of lines, we said slope was equivalent to the angle with the positive x-axis. Same sort of idea. Okay, so some notation. Magnitude, well, another name for magnitude is absolute value, and that's exactly the symbols we use. So it looks like we're saying absolute value, but the magnitude of our vector, I could write it as P with the tilde underneath. I could also write it as PQ, so obviously they're going to be equal. We're talking about the same thing. That's the size of our vector. Opposite, or more commonly called negative vectors, are vectors in opposite directions. If PQ is our vector P, then QP would be negative P. It's just going the other way. Parallel vectors will have the same slope. Well, they're parallel. That makes sense. So in other words, that vector PQ would have to be parallel to the vector QP. They're going in different directions, but they still have the same slope. Then you've got this really strange vector called the zero vector. And it's not actually a vector to look at, it's a single point. Because we're saying we're going from P to P. So really, it's just a single point. It's an unusual vector because it's got no magnitude. You haven't gone anywhere. And because you haven't gone anywhere, then you can't say what direction it's going in, because you haven't gone anywhere. So it has no magnitude and no direction. So because it has no direction, it's actually parallel to every vector. Scalar. Well, that's just the size. So it's a magnitude, no direction. It's a real number. Now, if I write something like this, and again, this is why it's important to put the tilde under the vector, so I know lambda, I'm talking about a number. It's not a vector. Whereas P here is the vector. I'm saying I'm getting P and I'm multiplying by lambda. So its size then would be whatever the magnitude of P is times that lambda. A position vector is a very special displacement vector. And it's the one that's anchored at the origin. So the tail's at the origin. It basically tells you what the vector is. So when you place it in that position, we know what the vector is. How do we play with them? So we add and subtract our vectors. When we're adding them, you always add them head to tail. You place the head of one on the tail of the other. So, right, there's vector A, and I'll add to it vector B. So I'll go, well, there, A, I'll add to it B. Well, a quicker way of getting there was simply going along this green vector, which would be whatever A plus B is. But addition of vectors, just like addition of numbers, is commutative. Just like when we say what's 2 plus 3, I get the same answer as if I'd said 3 plus 2. No different. So I could have said, oh, actually I've got the vector B, and I'll add to it the vector A, and let's have a look at that one. There's B, A. We get the same green vector of A plus B. Another way of expressing that. So vector PQ, there it is, PQ. I could have added QR to that, and I would have ended up with PR. Just have a look at that. Effectively what we're doing is when you see that they're added together, and you see how they've both got Q, it's like Q are next to each other, you can sort of smash them together, and the Q goes. So PQ plus QR is PR. So subtract them, so instead of placing them head to tail, we now place them head to head. Another way of thinking about it, and probably I think a better way of thinking about it, is add the negative vector. So you're still thinking of adding vectors, but I'm adding the negative because we know a plus minus will be a minus. So there's A. If I want to subtract B, I'm say, well, there's A, but I'm going to add the negative vector. So it's going in the other direction now. And when I put those together, there's A minus B. Now, what ends up happening is the A plus B and the A minus B end up being the diagonals of a parallelogram. There's A plus B, and I could have written it as B plus A. Creates a parallelogram. Opposite sides have to be equal and parallel because essentially they're the same vectors. So we know they're equal. Got to have the same size, got to have the same direction. So one diagonal is A plus B. The other vector is, well, the way I've drawn it is A minus B. It could also be B minus A if I say the direction's the other way. See, whenever you want to know a vector, it's head minus tail. So have a look at where it's going to, head minus tail, and that tells you what the vector is. So that's addition and subtraction. How do we multiply vectors? Well, initially, let's just multiply them by a number rather than another vector. So if I want to multiply, all I'm doing is I'm multiplying it by a real number. So the only thing that's going to happen is it's going to change the length of the vector. The direction's not going to change. So there's A. Well, 2A would be twice as long. That one there would be minus a half A. It's half as long, but it's also in the opposite direction. So it's minus a half A. But all of them are going to be parallel because, as I say, the actual direction, other than the one going in the opposite direction, is the same way. Let's have a look at this little question. So ABC, triangle, and then they've defined some of the things for us. So AB we're going to call the vector A, AC the vector C, P and Q are midpoints of those, and R is there, but what we know about it is the vector RC will be twice the length of the vector BR. First thing they want us to do. Well, what's BC and PQ, but just in terms of this A and C. So BC, head minus tail. In other words, it's the vector AC minus the vector AB. Well, C minus A. PQ, right, I want to go from P to Q, head minus tail. Well, AQ here would be half of AC. They told me that was a midpoint. And similar with P, I know that's going to be a half of AB, so I've got a half of C minus A. Well, compare those two, what do we notice? Well, basically, they're the same vector, but one's half the size of the other. So I know that the vector PQ is half of the vector BC. Well, what does that tell me about a triangle? Well, it tells me that if I join the midpoints of two sides in a triangle, it's always going to be parallel to that third side. Because what we just said was that PQ is half of BC. So the direction's the same, they're parallel. But the other thing we just saw, join up the midpoints, that's going to be half as long. So that's a feature of a triangle. What about BR and RC? BR is a third BC. Well, why do I know that? Remember, they told me that RC was twice BR. So BR must be 1/3 of that whole vector BC. So let's sub in what we found. We know AB is A, BR, we're saying that's a third of C minus A, playing around with it. It's just like algebra. Whilst they're not pronumerals, I can still use the same maths that we use with pronumerals. They're still like terms, and I get that it's 1/3 of 2A plus C. As a little introduction to the world of vectors.